Hi, let's take a look at this problem. This is the first one of the exercises that were assigned to be solved during the practice sessions, referring to thick shells. And the problem says like this. So it says that a thick cylinder with an internal radius of 10 centimeters and external radius of 16 centimeters is subjected to an internal fluid pressure of 70 megapascals. They're asking us then draw the variation of hoop and radial stress in the cylinder wall. Also determine the maximum shear stress in the cylinder wall. Let's see what's the problem telling us or giving us first. Just as a description, I have written down here or copied here for the formulas we had in the lectures for the circumferential stress or hoop stress and then the radial stress here. And something to kind of notice is that they are pretty much the same in formula-wise. So if you check how they are arranged, all the terms, they're pretty much the same. The only difference they got between them is the sign here joining them. But that's an interesting just point that I wanted to mention. Now here I have drawn the cylinder with the data that it was given in the problem. They said, well, internal radius 10 centimeters, external radius 16 centimeters. Pressure, so that pressure is something that is going to be kind of in here, yeah? So the internal pressure is going to be 70 megapascals. So I should write this a little bit better. Just wanted to make some sort of megapascals. Yeah, right there. So it's kind of, let me see, it's too much. I could use this one here. So kind of in here, 70 megapascals, all in here in this internal area. Sorry, yeah, internal section of the cylinder. Now, in this case, what is being asked is very straightforward. So we just need to take these formulas, substitute the values, and get the general formula for each one of these stresses variating across the radius in the wall, and then make a plot of it. And then in the end, apply the shear stress formula with these two stresses to get the value of the maximum shear stress. So let's do that. If I take the first formula for the hoop stress, circumferential stress, so what I'm going to get here is that every term that is associated with the outer pressure in the problem or possibility of outer pressure is going to be zero, because now we get that internal pressure, if I call it like that, PI equals to 70 megapascals. I got the external pressure, PO is 0 megapascals, because it's not referenced to it. Then we have RI, internal radius is 10 centimeters. But something interesting here is that we're working with megapascals, so that's kind of newtons per square millimeters, and then or related to square millimeters. So we need to work here with 100 millimeters. And then the other radius is 16 centimeters, equivalent to 160 millimeters. One important step before jumping into substituting the formulas is that we need to check if this is really a thick cylinder. And to do that, there is the formula also given in the lectures. Let me just put it out. That says that, well, if you want to know that if this is a thick cylinder, so we could use all the theory we have been talking about, well, you have to validate that the thickness of the wall divided by the outer diameter of the element has to be larger. Let me write like this, larger or equal than 1 divided by 15. This can be translated into, well, the thickness of the wall is just the difference between the outer and inner radius. So it's going to be 16 minus 10 centimeters. And we can leave it in centimeters because all the measures we're using here are represented in centimeters divided by 16. So this is going to be, if I make that calculation quickly, it's going to be 16 minus 10 divided by 16. That's 0. I got a wrong number here. 16 minus 10 divided by 16. That's 0. Here, 0.375 centimeters. Oh, sorry, this is non-dimensional because the centimeters at the top, centimeters at the bottom. And that's obviously kind of larger than 1 divided by 15, because 1 divided by 15 is 0.067. 0.067 here. So we got a green light to use all the theory we have been talking about in thick walls. Awesome. Now, yes, let's talk about the formula. We got here that if we wanted to use the formula for the circumferential stress, so we are going to get that all terms related to the outer pressure, like this one and this one, are going to be zero because it's zero, the outer pressure. So if I make the kind of the formula complete here, it's going to be something like this. So it's going to be Ri squared times Pi. And this is going to be divided by the square of the difference, or the difference of the squares of the radii, plus and R1 square, R outer square, times Pi. This is also going to be divided by the difference of the squares in here. And this term is going to be multiplied by the reciprocal of this term here. This is equation 1. Equation 1. After substituting the after considering that there is no external pressure. Now for the radial, let's do it just at the same time. Let's do the radial stress. And what I'm going to do is I'm going to copy this one because, as I mentioned, the only difference between those two equations is the sign joining those two terms, the one presented in between. We put it here, and I'm just going to delete this sign, put this one here, and this is going to be equation 2, equation 2. Now, if we want to just lay out everything, so we just come back and substitute terms, so we can say, well, let's answer the last question, which is, what's the maximum shear stress? Well, the maximum shear stress, represented like this, it's going to be what? Well, it's going to be the difference between the maximum circumferential stress minus the maximum radial stress. Let's remember that when we order these stresses are similar to the principal stresses in the state of stress tensor case, then sigma circumferential stress is considered like the sigma 1, and then the radial stress is considered like, the other, well, I believe was the minimum, the sigma 3. Let me just check quickly to validate that. It was when ordering those stresses, we got that, yeah, sigma radial is like the sigma 3. So this is equivalent, or these are equivalent to, this is equivalent to sigma 1 as principal stress and equivalent to sigma 3 as principal stress. And this is going to be divided by 2. Okay. Perfect. So I'm going to jump to GeoGebra just to have an idea of the graph of these, because that's what they're asking me. What's the idea of the graph? And then we're going to use GeoGebra also to populate certain equation to get what are the maximum circumferential and radial stresses here. So let me jump to that right now. All right. Actually, I should put it here. Yeah, it's better. Okay, so we get the first formula here. I'm going to write it down. I'm going to write like f of x to say this is a circumferential stress, and that's going to be equal to, let's define first the term. So we have pi, and that's equal to 70. No, it's not liking it. So p internal, equal to 70. Yeah, oh my God, internal there. Then radius internal equals to 100 millimeters. We're changing from centimeters to millimeters, and we got then radius external 160 millimeters. Let's enter. Let me change this to I, small I, lowercase I. Perfect. Now let's call this fx as the circumferential stress, and I'm going to write it like, it's going to be copying directly from what we have written before. That is r I square, then that's times p internal. Actually, this all has to be divided by, let me put it like this. It's not letting me, so let me just start from the beginning. Just bear with me. So now it's better like this. Our internal square times pi internal divided by the square difference of the squares. Not that one. Oh, I'm messing things up here again. Let me put it down here. So Ri square times P internal. This is going to be our outer radius square minus inner radius square plus another fraction here that is going to be our internal square times our external square times P internal. That's going to be divided by, again, the sum of the squares here minus Ri. And this is, again, the reciprocal of the radius. Let's call it x because we're working with fx, so let's call it x squared. There you go. Now we have already some charts here, and that's nice. But let me write at this time the other equation for the radial stress. So let me select this one, and I'm going to call this one gx. So they're going to be pretty similar. Let's remember that the only change is going to be that sign here. There you go. And now you see this is the chart. If you can follow this, the green line is going to be the circumferential stress. And for example, if we go from the radius of this one here, 100, so it's something like here. And if we go to 160, it's something like in here. And then interesting, for example, and it matches the condition that for the radius, the outer radius, which is 160 millimeters, and here, and that's the cut point between the root of this blue line representing the radial stress. Now, but let's get what are the maximums of these stresses. So let's get the stresses at the end. So circumferential stress at the inner radius is f of 100. Circumferential stress of the outer radius is this much, which I'm going to convert to that. Then we have radial stress at the inner circumference is minus 70, which is clearly the case because it's the internal pressure in the radial stresses. Remember that in the end, in the streams, they match the outer or inner pressure depending on the case. And then in the outer, well, in the outer has to be 0. So there is no other point there. So it matches everything. So let me go back to OneNote, and I'm going to take a screenshot of this one here because we're going to use it from here to here. What was the 70? Yeah, this one here. Perfect. So let's go back to OneNote and see how things look like. So let me draw first. Or what they're asking is to draw. What about if I stretch it? Does it look too bad? Well, no, it doesn't look that bad. So what we have here is, I'm going to draw the limits of the cylinder. So at 100, I have this limit here. Then at 160, I have this limit here. Actually, that's not 160. So 120, 40. So it should be something like just where it is touching this. And then we have our Cartesian coordinate system that we can represent like this. So this is the kind of in the direction of the radius. This is in the radial direction. And then this is the value of the stresses, being this one, the green one being the circumferential stress of hoop stress, and then the blue one being the radial stress. Now, I didn't get the maximums here because the maximums were, we go back to GeoGebra to check it. So in here, I'm going to have, let me mark this line here. And let me mark also this line here. So we have a clear reference. Also, let me complete this chart. Start from here, and we can get this one here. Although it's not that necessary because we already know what's the value here. Okay, so we have 0. Then we have at this point, at the end of this stress, is going to be 89.74 megapascals. Write it better. Could move it. I have here 159.74 megapascals, and I have here minus 70 megapascals, which coincides with the internal pressure. And this is kind of the wall. Perfect. Now let's calculate. Well, now we got what are the equations of the hoop stress and radial stress. Then we got also the plot for sure, as we are seeing it here. Now let's calculate this shear stress, the maximum shear stress. A maximum shear stress says that, okay, you want to calculate the maximum shear stress where along the thickness of the wall you want to calculate that. Well, it has to be where the maximums are found. The maxima are found. So, and we're talking about the internal radius. So if we look at the internal radius here, so we need to take care, or we need to use this one here and this radial stress here to calculate the maximum shear stress. So let's do it. So maximum shear stress, I'm going to come back to the formula, and that's going to be 159.74 megapascals minus plus 70, because minus times, well, minus is plus, and then we have this one here divided by 2. And that's given me, if I make this quick calculation on the 59.74, 59.74 minus plus 70 divided by 2, that's 114. Let's write it down here. 114 times 0.87 megapascals. And there you go. Is pretty straightforward. Just a couple of checks. For example, checking that this is really an applicable example, meaning that is a thick wall by taking into account this condition. And another check is that the formulas, when we do the whole simplification of these formulas, meet certain parameters. But for example, in the radial stress, the internal radial stress equals the internal pressure, as it is happening here in the calculations, and then the outer external stress equals the outer pressure, which is 0 in this case, so it matches everything. And now at the end, using the maximum values found, we can calculate what is the maximum shear stress here. And that's all the exercise. So it's pretty straightforward, pretty simple, just application of the formulas, and there you go. I hope it helps, and then we'll try to do another one of the same kind of nature. Thanks.